let's focus on the marine applications. What are the physics tools that we provide for simulation of marine applications? Each of the flows that you have seen in the videos that illustrate these different situations that ships can find themselves in, obviously are highly turbulent. So we need the very accurate turbulence. We have a wide portfolio that can address different situations. One of the most notable is generalized K omega turbulence model, or GECMO, which is based on the Rand's approximation of turbulence. We also have a variety of scale resolving models that are based on LES methods and the hybrids between the LES and RAMS. Typically, LES is used in the highly turbulent environment for extracting the effects of turbulence, such as noise, or simply looking at how these effects of turbulence impact the structure of the waves. And we have RAMS methods that are used together with the scale resolving method in the boundary layers. So we could have LES-RAMS type of hybrid, which is highly computationally effective. And in addition, we have hybrid models that treat the situation where you could have laminar and turbulent flow occurring at the same time. KKL omega is one of the most notable, and gamma R theta as well. So this is one example where you can see the turbulent flow in a cross-section of the flow domain, where the major turbulent structures are recovered and visualized by using the Vortex core visualization tool. Then, of course, you will have interaction between the fluids and solids in an environment where you have liquid and gas and the free surface in between them. In order to address that type of situations, we have both Eulerian and Lagrangian framework multi-phase model. Volume of fluid is the most important tool here because it tracks the interface between the liquid and gas and provides accurate simulation of waves and how they interact with the hull, as shown in this video. We have discrete phase models that can be used for tracking the droplets. Eventually, the waves crest and they break into smaller droplets and similar structures. Discrete phase can be combined with the volume of fluid method in order to capture these breakup phenomena. And we have cavitation models for situations that involve the work of the propeller and the related effects. In addition to turbulent and multi-phase simulation, you also need dynamic mesh adoption with the PUMA methods for mesh refinement in polyhedral cells. We also have the 6 degree of freedom solver, which is used for simulating arbitrary motion of the vehicle in contact with the water and air. Overset method is used for simulation of bodies that are in relative motion with respect to each other. And we have additional dynamic mesh methods such as sliding and deforming mesh. The additional features that are needed for this type of simulation is the ability to take this very detailed model that could take hours or perhaps a few days and extract the essence of it into a reduced order model, which can then run multiple degrees of magnitude faster than the CFD model, and yet retain and utilize the major or the main findings from the CFD model. Often we need to do fluid structure interaction type of simulation that allows us to resolve the complex wave-body interactions. The motion can be studied in both time and frequency domain, and log generation for structural response is an important feature that is provided by the CFD tools.